Alright, let's get started. So just the timeline moving forward. So today we've got the final exam review. Then the presentations again, just to recap. So originally I planned to do these in lab, but we want to experiment with the potential for something a little more innovative that allows for 475 maybe to be taught online sometime. And so now you upload video presentations. This could be, so you notice when I record these lectures, sometimes I just do slide overlays over here, or I record a whole video from this side. Or you can use in PowerPoint, you can actually record audio right within PowerPoint. However you feel best represents your presentation is fine, but basically a 10-minute presentation. It could be slides, it could actually be a combination of slides, and you may be alt-tabbing over to Arena to actually do a demo. However you think makes your argument, but basically in 10 minutes you upload that presentation to Canvas. And then at 5:30 on Wednesday, that's the due date for those. So that's the last minute of the last lab section. Then peer evaluations will automatically be assigned by Canvas. And so every student will get assigned 3 presentations, or 3 other groups. And then between then and Saturday, they just have to watch those presentations. There's a rubric. So when you go into the assignment, you click peer evaluations and then show rubric. And you can sort of score the other students. The other groups don't know who's scoring them. That's anonymous. And then I will take a look at those. And based on your peer evaluations, then that's what, if you've done your 3 peer evaluations and looks like you've sort of faithfully done it and not just, clicked all of one row, then because there's an opportunity to leave a comment like, oh, I liked the way you did this or something like that, then you'll get the attendance credit that's in the syllabus for the presentation, and then you'll be done with your presentation. Yeah.
Is there anything in particular you're looking for on the presentations in the final report?
What do you mean by in the presentations in the final report?
What in particular are you looking for from our project? Not overall, but in terms of conclusions and analysis.
Your presentation. So there's a question in the discussions about what I mean by a complete presentation. So I want your presentation to present the problem, why there was an interesting problem to study, the basic methodology. You don't have to go into the details of why we chose every single block, but the basic idea that we modeled this as a basic inventory management system, but we added in this other part here, and then in doing that, here is our simulation of the as-is system, and here is the change that we decided to make. Or maybe you have maybe you weren't doing sort of an as-is versus change. Maybe you're trying to better understand a very complicated system where the bottlenecks are and things like that. But you sort of present roughly what you did there and then the results. So here are some data. Great if your data has confidence intervals, because we could have learned that now we're all fully in confidence interval mode. And so then here's some data showing our as-is data versus our evaluation simulation. As you can see, they're different, and then some conclusions. And so we've concluded that this system has clear performance benefits over this system, but we know that the costs of implementing this system are going to be approximately X based on a Google search, and we know the benefits are going to be approximately Y based on multiplying the throughput by the average cost of the product or something like that. And so even though there is a increase in productivity, we don't actually recommend making this increase because it would be too costly, something like that. So something that tells a whole story of why there's a problem, roughly what you did to solve it, what the data that you got out were, and then what conclusions you drew. And so just wrapped up in sort of, you can imagine 2.5 minutes for each one of those. If you'd like to distribute that among your 4 members, that's fine. But if you find that there's a better allocation of effort, then that's also fine. So we want it to sort of just kind of flow well. And so it doesn't necessarily mean that you have to be keeping track of time, all right, now switch or something like that. So yeah, and you don't have to go over things like detailed issues about the input modeling. You can say like a lot of times students are tempted to say, well, so for the for the arrival process, we modeled that and we found out it was an exponential, and here's the histogram that shows that's true and all that. And that might be useful in the final report for extra scrutiny, but for the purpose of the presentation, does that add much to your story? Because at that point, you could say, when we modeled this, we found that the arrivals were, you could just say that you found that the arrivals were exponentially distributed, or you leave that out entirely and just kind of, for the presentation, we'll take it on faith that you did the input modeling right, and then we'll double check that when we look at the report. Does that make sense? So just how would you make an argument? You're going to do this in a job frequently. You're going to be tasked with something that will take you several weeks to do, and then you'll have a group report where you'll all get together in a conference room, and you'll have about 10 minutes for everybody to summarize their progress and get feedback from the rest of the group. That's how you can kind of view this. I'm presenting to my stakeholders a condensed form of what I did and what results I got, and whatever I need to connect those two together convincingly. All right. So that all happens kind of midweek, and then the lab report will be due then again Saturday night. Same thing with those peer evaluations. That's just a 4-page report. The format is online. That 4-page does not include the title page. It also doesn't include the appendix. And so your 4-page report, there's this particular structure that I think I actually have in a slide or two. But that structure, it sort of, again, tells this story. It has an executive summary. It outlines the problem. It outlines the results and the conclusions. And you may not have to include, say, all of your arena model in there, but you would want to put all your arena model in the appendix then. So the 4 pages are sort of how you're making your argument in a little more detail than you do in the presentation form. And then you can refer the reader if they want to see the full model. Like a lot of times your full model, if you look at the example project report, they did, I think, 4 peaks. And they have a lot of repeated sections that in their big model, they use over and over again, but they only kind of had to present once in their main document, and then I think their appendix had the full model, and you can imagine a similar sort of thing. And then the final exam, so this is distributed between this week and next week. So the last regularly scheduled class is what, this pre-take, and then during finals week on Tuesday is the retake. I've been emailing the TAs almost daily, asking them to make sure you get grades in so that when people have their pre-take scores, they'll be able to have confidently say whether they want to come in to do the retake. And I actually have to be on a plane during the final exam, so I can also try to do my best to help along with that. So that's kind of the schedule here. It's the best of the two, exactly like the midterm. We'll talk about the format here in a second, but this is, again, basically the timeline for this week. Not a whole lot left. The final project reminders. So, it's a little late to make major changes, but try to frame your arguments in terms of why you made this simulation because you couldn't do it in another sort of way. And so highlight to me what was interesting about your system that you couldn't kind of reason about without a simulation. Like you said, well, it seemed like if we would add another server, this would happen normally. But because there's this extra constraint in the system, it's difficult for us to see if adding another server will have the desired effect. And so we had to simulate it. So that sort of thing. In the past, I've said that like a good heuristic is that if your simulation is complicated enough that there's like an ugly bird's nest in the middle that you're tempted to highlight with a submodel and hide in that arena submodel, that's probably a good sign that you've added enough complexity to kind of elevate yourself away from just simple 470 type methods. But I'm not formally requiring a submodel, but you will be sort of judged on whether you've kind of addressed a problem that is interesting enough that to actually warrant going through the whole process of doing a simulation. This is the report format. This is also online. This basically from 2 through 6 is all 4 pages, so that'll go by really quick. And anything else that like you feel like you had to condense here that for completeness you want to include, you can put in the appendix, which is unlimited. But they're mainly going to read parts 2 through 6. And then also include your DOE or file or files. So you might, it's totally reasonable to say have an as-is system in one DOE file and your experimental system in the other DOE file and upload both of them. But make sure that your report stands alone. So we want the DOE files there just in case we want to check anything but we want to make sure that you could read the report and be happy and convinced without then having yourself go and check out the DOE. So it would be a self-contained report. And there is a sample final report that is online. Then 2 other surveys. So there's one you know about, course evaluations. Those are due at the end of this week. But then this is kind of hinted at, since we're doing this retake study this semester, then after the retake exam during finals week, then we'll unlock a survey which asks you similar questions as the midterm survey. So, why did you take the retake? Why did you not take the retake, et cetera? And this goes into a study that we're working on. If you're interested in being a part of that study, then this will automatically get announced on Canvas, just like it did in the midterm. But that doesn't happen until the minute that the retake during finals week ends. And then that will be available basically until grades are due. And so that morning of the 16th, then they will send me a list of who filled out this survey. I'll put that up into Canvas, give all those people the 4 extra credit homework points, and then I'll submit your grades. So that's the process there. So 2 surveys that are both important to me, the course evaluations and then this extra credit one. This one won't be available till right after the retake during finals week. All right, so any questions? Okay, so how to study and how to prepare. Again, we got 2 tests that look identical to each other, 75-minute exams. I've completely made the pre-take. It's printed out. It's ready to go. I am now making the retake, so I sit the pre-take next to it, and I make sure they have the same number of questions, and I basically say, how do I make a question like question 8 that is very similar or is sort of roughly similar in where it comes from the course and is of similar difficulty, but is a definitely different question. And so that's kind of what I did during the midterm as well. So if you've taken the pre-take, then expect the retake to be very similar in format and in feel. Closed book and closed notes, two-sided. I say handwritten, but really I just mean kind of hand-produced. So you can type it up, it just can't be photocopied. Formula sheets, just like the midterm. Each exam will have an A and a B version, so it'll be kind of checkerboarded through the room. We'll use Scantron. It's going to be a very similar format to the midterm. Actually, you might have looked online, and it says that the final is out of 42 points. The midterm was out of 31. The first 10 questions on the final are just making sure you filled out the Scantron correctly. So those are real points. And so it's not, I didn't actually extend it very, so most of the answers to that will be bubbling in A for yes. So it'll be like, did you bubble in your last name? Yes. Did you bubble in special code K? And I always do that because I will be here for finals week, but I have to let the TAs proctor this week. And so I'm always nervous that I won't be there to make sure that all the bubbles came in when I'm turning them in. So I've added this kind of sanity check, but that's why there's an extra 10 or so questions. They're just there to make sure you filled in. So it's basically the same length as the midterm. Maybe one more question, but the questions are not necessarily harder questions or easier questions. And then I think the extra 10, you effectively buffer your score because now nobody's going to get lower than a 25% because everyone will fill out these first 10 questions correctly. I hope. You can get them wrong. So if I say, and I'm not going to, I won't give you any, pity points because I asked, did you fill in your last name? You said, well, no, I didn't. I guess I'll fill no. Don't do that. If it asks you, did you fill in your last name? Fill in your last name. So exams were 20% of your grade. So a plausible final exam structure. So this is probably, again, I have to squeeze this down into a Scantron format in 75 minutes. But what I start with when I build an exam is I want things that roughly have about, say 12 to 15 problems, if this was ideal, if I had the full 110 minutes, with multiple choice and true-false questions that sort of will cover over concepts from DES fundamentals, basics, what is an entity, a resource, input modeling, a couple things about can you choose the right probability distribution, do you know the difference between this whole steady state and terminating stuff, performance stuff, VRTs, and then there are definitely questions about arena. So I might show you a diagram and say, what is the purpose of this block? What is the difference between this model and that model? So arena will definitely show up on there. And then some quantitative stuff. And so maybe some short stuff where, maybe I say you want a certain confidence interval. So choose the number of samples. So here's some pilot data, where maybe you have to calculate, or maybe I give you a sample standard deviation. Based on that, if I want a confidence interval that's this width, can you choose the number of samples? Do you know the difference between an antithetic variant and a CRN? So if I gave you a bunch of random numbers, would you be able to apply them appropriately? Whereas in a CRN, you'd run the random numbers maybe into the same two inverse cumulative distributions functions. With an AV, you'd have to know that for every random number, you do 1 minus that random number, and then that pair you run into the inverse CDFs. Evaluate statistical power. I might give you a operational characteristic curve, and then have you calculate if I want 80% statistical power, how many samples do I need, or if I have this many samples, what's my statistical power? And then some arena syntax stuff. So I might say if I wanted to simulate a discrete probability distribution with these masses, what disk line would I use? I might say, like, here's the first 4 numbers, what's the 5th number or the 6th number, something like that. And then maybe some statistical tests. So I might say, well, can you do a goodness of fit test? So I might say, well, what about if you look at, I think, the sample final, I think I said, well, here's a bunch of data and some 9 data points, and here's a triangular distribution. I think these data are, where the triangular distribution goes from 0, has a mode at 4, and a max at 4. And so based on that, can you do the chi-squared test, or can you do the, in that case, it would be a Komagata Smirnoff test. Hypothesis test of relative performance. So can you do a basic paired t-test? If I gave you a CRN situation, would you know to subtract and then take the differences and then do a very basic t-test of, are these 5 differences significantly different from 0? And then maybe one design problem where I say, design a random variate generator. So here is a desired CDF. Here are some random numbers. Give me the first 3 values that would come out of a random variate generator, and I might modify it a little bit just to make it more post-midtermy and add sort of a link to maybe CRNs or AVs. Like, so here maybe are 2 random variate generators, and maybe you have to develop the general formula, but maybe you evaluate it for 2 different parameter values, and you'll plug in, use CRN to measure the difference in those between those 2 variates or something like that. So you can imagine things from the midterm kind of modulated with things after the midterm. But remember, I have to squeeze all of this into effectively 32 questions, and then do it all in a Scantron form. So this is in my ideal world. If I had all 110 minutes and maybe even some short answers, this is what I start with. And then I think, how can I make that Scantronized, and how can I squeeze that down into 75 minutes? Practice problems. You've got these ICA practice that are not graded. I mean, you can see the grade, but they're not scored. We've got the sample midterm and sample final. There are solution sets on Canvas. There are these homeworks. I would say if you're prioritizing looking through the homeworks, homeworks D2 and G3, I would just sort of practice them as they are. For homework C2, look at like the KS test that's there, but think about how would I generalize that to other distributions, not just a Poisson distribution. If I gave you an arbitrary probability mass function, how would you do that homework with that arbitrary probability mass function? Definitely remember your hand simulation. So if you're, even though you're not going to do hand simulations moving forward in your life probably, it's still important to know what's going on behind the scenes when the sim runs. We've had people email me about their projects, and their sims have gotten into these kind of infinite loops. And that's because there were loops where there was an activity that didn't have any duration. And so whenever it scheduled things in the internal future event list, it was effectively scheduling events that happened instantaneously. It just got stuck. Yeah.
Would you say that the exam is more theory-based or more computational-based?
Well, I mean, I don't know exactly how to weigh things like that. I mean, there's going to be questions about arena. There's going to be questions about basics of modeling. And so I would say it's fair. I mean, I'm not going to ask you to prove like the central limit theorem or something like that. But I might ask you to say, well, if I've got you know, a sum of different independent random processes, and I want to come up with a model just out of, you know, that I think might fit before even looking at the data, then you'd have to say, okay, well, by the central limit theorem, since that is a sum of independent random variables, that's probably going to look like a normal if I have enough of these things. So it's going to be a little more practical, but it definitely might call upon things like that. There are additional problems from the book that I might recommend looking at. I put some solutions to some of these problems that are posted on Canvas. All this is under the final exam module, Unit N. And then as you're looking through the lectures, if there's something that you need clarification on that I just wasn't that clear on in the lectures and you need extra help and it's the last minute, then on Canvas, every lecture has an associated chapter with it, or most lectures have an associated chapter with it. And so I try to follow the narrative that they give, that they put in the Banks book, the chapters, but I very much kind of built a lot of my own content from that. And so you should find the same topics there, but probably presented in a different way. And so if whatever I'm saying isn't quite resonating with you, and you know, so you're like, yeah, something in lecture B1 I just really didn't get, even though he said it like 3 or 4 times, you just didn't quite say it differently enough. And so let me look in chapter 3, and maybe Banks does it better for you. And so there's that additional reference there. So that's just general my study tips. And so at this point, I'll ask for questions. I'm happy to take open-ended questions. If there are no questions, then basically the way the rest of this is laid out is I just kind of highlighted in, I've taken sort of all of the lectures throughout the course and compressed them into one lecture-length set of slides. And I can just flip through those and see if they trigger any, you know, good memories or bad memories that might trigger questions that you have. But before I do that, I just want to see, are there any general questions? Yeah.
Can you go over an example of finding the number of replications?
Finding the number of replications, sure. So let me maybe plug in here. So don't look at that. All right, that'll do. All right, so question was like, how do you choose the number of replications? So there have been 2 basic approaches that we've talked about here. There's the kind of power analysis. And this was like that homework, I think homework, I don't remember the letter, if it was C2. But this was the one where we used the operation, the OC curves. And you basically specify a statistical power. And then given the statistical power and the desired effect size, you can choose the number of samples. I'll tell you ahead of time that, that on the exam, I didn't provide a OC curve, and so I am not going to ask you to do a formal power analysis, but but I will ask questions about power analysis. And so with that in mind, the quantitative things that you would do is I would say that the choosing the number of samples for a desired confidence interval width. So you might specify a confidence interval width of, so you say you like want a half width of 2 or something like that. And so we just have to remember what the half width formula is, and we say, well, the half width is the sample standard deviation over the square root of the number of samples times t alpha over 2 times the number of samples minus 1. And so if we knew the sample standard deviation and the number of replications, we could then look this up in a table and calculate the half width. And so if I instead say I want a desired half width and I give you a pilot data that has a sample standard deviation, so I know ahead of time that from my data, this is what I estimate the standard deviation to be, I want that to be the half width, then in principle, you could be able to calculate this, but this gets a little ugly here, and so effectively what they've done is they've approximated the half width formula by a z value instead, because as r goes to infinity, the t distribution goes to the z distribution. And so when this is if you forget the formula for, if you didn't write it down in the formula sheet and you want to make sure you know how many replications you get, as long as you have the half-width formula, you can kind of solve for what you need here. Because yeah, question?
Yeah, can we bring tables to the exam, like the tables for the distributions?
Any like solid, hardcore numerical tables you need, I will provide you in the exam.
Okay.
So I would recommend just keeping it to formulas, protocols, things like that. So for here, the half-width formula, it's got like squares and things like that, and all it really does is it just solves this expression here. So if you like did, the half-width divided by that z-score times square root of 2 or square root of r. I'm sorry, that's not what I meant to bring over. And then that whole thing divided by the sample s, and that is equal to 1 over square root of r. Then you flip all that things over, and you think you have square root of r is equal to s over the half width times z alpha over 2. And then if you just squared that thing, then you'd end up getting that formula that comes out of the book. And so if I square this, then I just get r is equal to this thing squared. And so once you have that formula, if I give you a standard deviation from data and I give you a desired half width, then you should be able to look up based on the alpha, this z value, and then calculate r, the number of replications that should hopefully give you that desired half width. Yeah.
So on using the z value instead of the t value, I don't know. So there have been multiple times, like for example in ICAs, where I'm not sure if we can replace the t with the z because I don't know if we have a sufficient number of samples.
I see. For this particular case, choosing number of replications to get a certain half width, you're going to always do it here because we're kind of assuming that we will eventually have lots of replications, and it would be really hard to not do it the other way because otherwise, if you don't know the number of replications, you don't even know what number to put here. And so you'd almost have to do this combinatorial search through every single t value for every number of replications. So that's the reason why it just gets swapped out here. But in general, if I'm asking you to calculate a half width, use the t value. Like there are, I think, no cases where I am okay with you replacing the t value with the z value unless it's this particular case.
I'll have a question on this. So what about cases where we've already run the simulation and we're trying to find what the additional number of samples we need is?
You can do this. So when you run the simulation once, that effectively is generating this value. And then, then you'll generate this R, it gives you the total number, and then you can subtract off what you've already run. There's a question over here.
Yeah, do you have to calculate the sample standard deviation through like a data set, or is it given to us?
Well, if I ask you to calculate the sample standard deviation, I promise I won't give you that many numbers to calculate. I would say that it's important to know how to calculate this, but that's kind of really low hanging fruit, and so that's kind of like a 380, 385 thing. I do want you to know that in order to calculate the unbiased sample standard deviation, you divide by n-1 and not n. But that's not going to be a major focus. I would make sure you know how to do that, but unless it's really interesting or compelling, I'm probably not going to have you give you 10 numbers and have you calculate a bunch of differences and a bunch of squares and do a bunch of averaging. But know how to do it, know the formula, and know why it's n-1 and not n. Yeah.
For the chi-square test, if you give us the mean, we don't have to do n-1 degrees of freedom, right? It's just when we have
When I give you a parameter, maybe mean or maybe anything else, but yeah, but the general idea is with the chi-square test, the degrees of freedom, and I can just write that note down, is that so for a chi-square test, the degrees of freedom are equal to the number of bins minus the number of estimated parameters minus 1. And so there's going to be, a chi-square test is a test of whether the data fit a particular distribution. Every distribution has a certain number of parameters. If I give you the parameter and say it has to be this, regardless of what the data are, then there are no estimated parameters. But there might be 2 estimated parameters. I might give you one, but not the other. Well, if you have to estimate the other, then this number goes up. So you just have to count how many parameters did I have to guess from the data and how many parameters were given to me. If they were given to me, they don't penalize the DOF. If I have to calculate from data, then every one that I calculate subtracts 1 more from the degree of freedom. Any other specific? Yeah.
Can we just go over briefly relative performance measures again?
The relative performance measures. So I can see. You mean paired versus 2 sample versus those? All right. So that's. I guess I can just write that. So relative performance measures. I'd say that there are, and I think I have a slide that looks exactly like this, but I'll just write this down here for emphasis. Relative performance measures is when you're comparing 2 or more things. And so if you're only comparing, there's pairwise, there are measures that have high power, but many assumptions. And the one at the top of that list is the paired difference t-test. And so this would be what you'd use, for example, if you wanted to use CRN. And a paired difference t-test is just that you're going to have outputs like I have a simulation model 1, and it has replication 1, and I have a simulation model 2 and replication 2, and that gives you a difference for replication 1. Then you might have simulation model 1, replication 2, simulation 2, replication 2, and that gives you a difference. And you have all of those differences, and then you're basically doing a 1 sample t-test against the hypothesis, the null hypothesis, that the expected difference is equal to 0. And so this is the one that you can only do if you run both models with exactly the same number of replications, and you pipe it and you pair them in some way. So for CRNs, you pipe in the exact same random numbers into both. And that pairing makes across the 2 different models, you lose independence. But if you take the differences are independent across the replications, and then you can just do a simple 1 sample t-test. So this is kind of the gold standard, and that if you can do this, you have the most statistical power. It can find the tiniest differences. And if it doesn't find a difference, then you have the most confidence that the 2 models are the same. So whenever I say high power, what I'm also saying is if you don't reject with high power, then you might actually be able to do the closest thing to accepting. So high power is what you want to look for when you really want to show that two things are similar to each other. If you cannot make these assumptions, then the next step is, in the pairwise case, would be to do a two-sample t-test with pooled variance. And so in that case, I'm just, I gave you formulas for this, so I'd recommend sort of, going back to those formulas for the degree of freedom. So this is degree of freedom. And the sample, the standard error of the mean here, which is like y1 minus y2. So I gave you formulas for both of these. And if you have formulas for both of these, then you can calculate a critical t statistic. Or you can actually calculate a confidence interval. And so your confidence interval is going to have a half width in all of these cases of this, of the formula I had before. So the standard error of the mean divided by the, well, actually, that's actually all it is. It's the standard error of the mean times the critical t value. And I'll erase this extra line here. So basically, if you know the formula for standard error and the formula for degrees of freedom, you can calculate a half width. You know that the half width is centered on the difference between the two means. So if you took the average of one model and the average of another model and subtracted them, that's where the half width would be centered around. And if you compared that thing to 0, just like you did with the previous pair difference one, then you could say whether one model is different than the other. But you can only do this if the two models have the same variance. And so this has a small assumption that two models have the same variance, but it's a much weaker assumption than the pair difference. And then the last pairwise one we talked about is if you did a two-sample Welch's test. And this is what you do for unequal variance. And there are basically very few assumptions. Effectively, all you're assuming here is that the two models are normally distributed. And if they're both normally distributed, they can have unequal variances, that's fine. There's another formula you'd have to look in your notes for the degree of freedom and the standard error. You can use that to calculate a confidence interval, and then you can use the confidence interval to evaluate whether the two models are different by comparing that confidence interval to 0. So those are all the pairwise ones. The only thing that I would say for more than two that I would recommend you remember is this Bonferroni correction thing. And so you might imagine that I could ask, so you're going to have a certain number of comparisons. So these comparisons might, so it'll be like saying that, well, if I only had two models, I'd compare one model to the other. But what if I had 6 models? And I'm not interested in every single combination, but I'm only interested in whether this model is different than these other models. And so in that case, I might only have to do 5 comparisons. And so the question would be is if I don't want to detect a difference in the family with a false positive rate greater than 5%, then what pairwise false positive rate should I use for each one of the individual comparisons? And that's just the desired false positive rate divided by the number of comparisons. And so with those, there's 3 different ways to do pairwise comparisons based on whether the samples are independent or not and whether they have equal variance or not. And then using those, then when you want to compare more than 2 things together, we have a method for you to get a desired family-wise false positive rate by dividing by the number of comparisons. And so that's kind of all of like relative comparisons bundled into 2 pages. Questions about that? Other questions? One more?
So I'm just going back to when we did validation and we were comparing the two different systems, I think on waiting time delays. So why could we not, so we said that our two different outputs, we were using the same input for the simulation and for the real output. Makes sense. But why could we not use the two sample t-test because of the independence assumption, but then use the one sample t-test when the two sets of data are not independent still?
When the two sets of data are not, so when you're doing validation, so I mean typically with validation, which is effectively a kind of goodness of fit test, you've got two models, usually a real model and a sim model, and if there's data going into the real model producing an output and different data going into the sim producing a different output, then there's no other choice. But in this case, you have to use a two-sample test. But if you have a way of running the data from the real system into the sim, then you have a way of pairing the outputs, and you could use a paired test. And a paired test is a one-sample test, because a paired test, means that you're going to take differences and then compare the differences to zero. So it's effectively a one sample on a difference. But you can only use a paired test or a one-sample test if you have a way of pairing them. And so in validation, it's usually going to be from real to sim, which will usually mean taking real data out of there and putting it into here. But if you might also do something like, I created a simulation model, and I think I could have created a better one, like it runs faster, but I want to make sure that it still performs the same way. In that case, you might run the same random numbers into it, and it's kind of like common random numbers. But in that case, I'm not using common random numbers to find a difference. I'm actually using it to find a similarity. So if you have a way of, if the inputs can be paired, the outputs are not independent. And if the outputs are not independent, then you cannot use a two-sample. I don't know if that, okay. Any other general questions? And a lot of things go back to fundamentals too, like just being able to look at a confidence interval and say, what hypotheses can I reject just by staring at that confidence interval? So, so make sure that, like if I were to give you a confidence interval on a real line, and I know that like this part of the confidence interval is at 3, and this one's maybe at 4.7, and it's centered wherever the average of that is, then know that everything outside of the confidence interval is rejected, and everything inside the confidence interval we don't know. So we can only reject things outside the confidence interval. Also know that if I gave you 2 confidence intervals and you wanted to do a pairwise test, but you didn't have the data to go back and do a proper pairwise test, then know that if the confidence intervals do not overlap, then the pairwise test would reject the hypothesis that they're the same. But if they do overlap, there's nothing you can say.
What if the value is right at the boundary? Would you reject or fail to reject?
Well, I mean, I won't give you such a pathological case on the test, there's basically in that case you're in one of these with probability 0 kind of corner cases where it doesn't like what it means by that you're at these like. So I mean, really, when we draw confidence intervals, I guess we should draw soft boundaries, because what we're not. It's almost like the question doesn't even make any sense. Like we can't firmly say. I mean, I would say that if it's right on the boundary, then p is equal to 0.05, and most people would say that does not meet that it has to be under 0.05. So I would say to be safe, consider this to be an open boundary, and it has to be inside the confidence interval. Or I guess maybe the other way around is that it consider this to be an open boundary, and if it is outside of that open boundary, you can reject it. In order for you to not reject it, I mean, I don't know. I'd actually say, instead of kind of going back and forth on myself on how but I'm not going to give you that case. And those are kind of cases that are more philosophical than practical. Yeah.
Sorry, I just have one more question. So if you had, I remember in lecture we were talking about like a situation where two different confidence intervals don't interlap, but if you double them, they do.
Oh, so there's a rule that if somebody gives you on a graph, let's say error bars, where these are standard error bars, so this is standard error, the mean, then the confidence interval, it is just double those. So a 95% confidence interval is just going to be, so this will be the 95% half width. And so that's just the rule that if somebody plots a standard error bar and you want to quickly say, well, what's the confidence interval? You can just double the standard error bar and get a good visual guess at what the confidence interval is. And then from there, you can use those same rules that I was saying, that if the two confidence intervals overlap, you can't say anything. So the example that I did in class is I showed that somebody might plot two treatments next to each other where their error bars do not overlap. But if you double their error bars to get the confidence intervals, you find the confidence intervals do overlap. So although this might look like a concrete example where they're different, they're actually not so concrete, and you really need to do a proper two-sample test.
So the difference was it's just the standard error. We're not actually looking at the confidence interval in that case.
Yeah, standard error is just trying to capture this. So every mean estimator is a sampling distribution, and the standard error is just trying to say roughly what's one standard deviation away from the middle of the sampling distribution. And so if the data happen to also be normally distributed and somebody just happened to plot standard error, because that's a common practice, if you want a quick estimate to kind of do a t-test in your head, you can double the error bars. But it's just meant to kind of help you visually process those data. Okay. Any other questions that have been lingering? All right. Well, let me flip back to, if anything does come up, I am happy to work any other problems. But let's just remind ourselves of where we've been. Stop me if you see something that brings up a question. But we go all the way back to, what are models? So it wouldn't be surprising to see a question about general models, like do models have to be quantitative? Well, apparently not. Fashion models, so like there are things that give us qualitative insights that are still models. So we still consider them to be models. Likewise, all simulation models don't have to be stochastic. You can have deterministic simulation models and so on. Simulation models typically are going to have these things. Hopefully everybody is much more comfortable with these terms. So expect to see heavy use of these terms, and then maybe terms that are more derived from that, like not just resource, but resource capacity. So how many resources are available? Resource utilization. How many of them are currently being used at the current time? Being able to sort of walk through these simulation tables, know about clocks, events, activities, the difference between activities and delays. Hopefully everybody has gotten to the point where they view activities as inputs and delays as outputs. Being able to sort of do a hand sim like this. And then, by the way, when you do a hand sim, it's identical to hitting the step inside Arena. And if you instead of hitting play, hit step, you'll watch one entity move one spot. And what you're actually seeing is Arena step through this event calendar. So be able to produce this event calendar, or if I give you an event calendar like I did on the midterm, be able to read it and be able to say things about it. So this is just reminding us how to step through, how to find the activities, how to find the service times, which are also activities, how to then find the delays, and know the difference between delays and activities. So very, very, fundamentals. So any questions about the fundamentals of activities, delays? Is any rusty to anybody? Yeah.
Just curious, like when you say that models can also be deterministic, what would you say it's kind of like in real life the ratio of stochastic to deterministic models?
And that's a hard question. I mean, I actually sometimes deterministic models are useful. So in IEE 477, those are models that are entirely deterministic. Those are system dynamics models. And system dynamics models are effectively capturing the mean behavior over long periods of time. So over long periods of time, we don't really care about stochastic fluctuations. And so a lot of people then say, well, if I can't really get the variance just right, then I'm just going to have sort of a deterministic approach from month to month. Like this is how I think the mean from January is represented in the mean from February. And those are very common. So stochastic are very common and deterministic are very common. And depending on your problem, you might use one over the other. A lot of agent-based models are deterministic as they execute, but are random in how they're initialized. So they're technically stochastic because every time you run them, you get a different output, but you're not actually drawing any random numbers during the model. So, but they can be deterministic or stochastic, is kind of the big point. Probability. So remember your PMET, your difference between PMF, PDF, CDF, and I would say inverse CDF, which is otherwise known as the quantile function. The general idea of using probabilistic input models, common distributions. So I'll go through a couple that you should probably know off the top of your head. So input modeling, this general idea that when we say stochastic, the word means we're using randomness not because we think the world is fundamentally random, but because it's easier to model realistic variation with probabilistic distributions than it is by coming up with deterministic models that capture that variation. So we're not actually saying the world is random. It may be, but we don't care. All we care about is it's easier to model it as if it's random in sim. So the distributions, be able to sort of tell the difference between continuous and discrete, because I might say, match up this particular type of data with a plausible distribution. And your first kind of guess should be, well, is this a continuous or discrete? And if it's continuous, then what continuous distributions do I know about? And vice versa with discrete. Poisson counting process, how it relates to these. So hopefully this will be kind of a review from, 380, 385, 470, those sorts of classes. But I'm happy to go over that. The distributions I would say that I would think you should focus on, maybe later I've got some of those, but I would say that, no exponential, no Weibull, no Erlang, no norm. Actually, yeah, all of these I think would be good ones to know. That long list that I give here, actually this is, I just kind of broke it out. So these I think are good ones to study. So I was afraid I brought in the full slide from this lecture, whatever lecture this was, D1. So in D1, I go through a bunch of different ones, log normal, et cetera, those sorts of things. But I'd say the ones that I think you should probably feel comfortable discriminating between for the final are right here. So if you're able to say that, like, okay, so this is a failure distribution where things don't necessarily fail at a constant rate. Oh, that's a Weibull. Oh, I see that this is a sum of things that fail at a constant rate. That's an Erlang. This is a inter-arrival time of independent arrivals. That's exponential. This is a sum of independent random variables. That's a normal, and so on. So those are good ones to know. On the discrete side, know that like a geometric is the number of tries until you get a success, given that your probability of success is p. So even statistical tests, I've said like if you run the same statistical test over and over again, eventually you will falsely detect a positive, falsely detect a difference from the null hypothesis. And you can actually model that as a geometric. How many statistical tests until I falsely detect a positive result? So I would sort of focus on these, and then the rest of them I brought up there, going to know going forward, but I probably am going to focus all my questions on these. So any questions about the probabilistic stuff, about any distributions, about the difference between different distributions? Yeah.
Gamma distribution?
So I don't think I put that up here. So for those that are interested, a gamma distribution is just an Erlang with a non-integer k. A gamma distribution pops up. It might be one of the ones, I guess, Arena's input modeling tool gives you, and it's just extremely flexible because it, just like the y-ball, it now has two continuous parameters. So you'll see that a lot. I'm not going to ask you about the gamma distribution. The gamma distribution is called the gamma distribution partially because it makes use of the gamma function, which is a generalization of a factorial to non-integer arguments as well. But if you know the Erlang, you kind of know enough, and if you know the Erlang, you're 90% of the way to knowing the gamma. Random number generation. So this will not be hit as heavily on the final exam, but you should still basically know about seeds and required properties and desired properties. Know that if I run a stochastic simulation from the same seed, it'll give me the same result over and over and over again. And that's like a feature, not a bug. So if you can understand that last sentence that I said there and feel confident with it, you probably know roughly everything that you should know here. It might be a good idea to brush up on the LCG and have that formula available just in case I ask you to generate a random number and then maybe modify it in a way that corresponds to CRNs or AVs. But I'm not going to go into great detail here. That's what kind of pre-midterm stuff. Random variate generation, though, definitely feel comfortable with your random variate generation, the inverse transform method, those sorts of things. That's like a key critical component of this course. Is that you come out of the course and you should know that if I need to generate a random number, if I can find its inverse out there, and then I can generate samples from it. This is how you generate samples from the normal distribution inside Excel. You look up the inverse CDF for a normal, and then you run random numbers into it. And so this, this general idea of being able to look for the quantile function, look for the inverse CDF, pair it up with uniformly distributed random numbers between 0 and 1, and get samples from whatever distribution you want, that is key. And so definitely feel comfortable with that, because I need to make sure you leave this class knowing you can do that. And so, summary of that, this is the big thing that I would take away from the pseudo-random number generators is this idea that every stochastic sim is independent because it comes from a different seed. It's like I have die that always roll up the same sequence. The only way I can get independent sims is by switching to another die that then rolls a different sequence. It looks random, but every time I roll the die over and over again, I get the same sequence over and over and over again. So in order for me to get an independent replication, I need another die. And that's like going through another seed. Know that in Arena, where there's that seeds element, and that's where you configure that, where you can say, I want a different seed, or I want my seeds to be configured as an AV or a CRN, etc. So this is just a reminder of the LCGs, and then this graph, like understanding this graph for the inverse transform method, that if I give you a discrete continuous, it doesn't matter. If I give you a CDF, then you can draw numbers from 0 to 1, as long as they're uniformly distributed, pipe it into the back end of the CDF, the inverse CDF, and then get samples from whatever distribution you want. That's like fundamental and critical. Definitely know that for the final. And then I just summarize how to do it for the continuous case and how to do it for the discrete case. So any questions on random variate generation, random number generation, seeds? Okay. So we've had a lot of questions so far, so I won't go through this, but this, I sort of put this in here as a canned class exercise, but so maybe do this on your own. Make sure that you're kind of comfortable knowing that this here could be a PDF, but it would not be a CDF. This here could be a PDF, but is probably not. This here could pretty much just be a CDF. Know here that this here could be a CDF, that this is not anything, this could be a PDF, and this could be an inverse CDF. So be comfortable if I was to show you these plots to be able to evaluate their CDF-ness. We've done actually exactly this example in class back when we first went over this stuff, so just make sure you do that. All right, then as we move into kind of post-midterm stuff, be comfortable with this plot. Know this basic idea that if you can have test distributions and alternative values coming up from elsewhere, how do we choose these thresholds, and what do we mean by true negative and false positive and all of that? So be sort of comfortable with either this graph here or a table like this one here, where you can say that if I'm in a world where the hypothesis is true, then if I reject the hypothesis, that's what we're referred to as a positive result, and in this case, it is a false positive, and that's what we call type 1 error. So be comfortable with these, and if you don't like this terminology, then this alternative terminology where you're saying the world is expected, the as-is model, the performance is as-is we'd expect, and then the world is different. Our simulation is better than the as-is model. And so if we detect the difference, but it's a bad difference, then we say that's a false positive. If so that's in the world as expected, but we think it's different, that's a false positive. And so that's a different way to interpret all of these things here. So if you don't like the terms type 1 error and null hypothesis or whatever, then you conceptualize it this way. But you should be comfortable with this idea of a positive and a negative, and what's a false positive and what's a true positive, and how statistical power is the true positive rate and type 1 error is the false positive rate. So any questions about the stats or the terminology, this graph? All right, so try not to, try to be able to form meaning. So instead of just saying reject the null hypothesis, if I ask you to reject the null hypothesis, I'm probably not going to say, is the null rejected? I'm probably going to say, are these numbers uniformly distributed? And so, so be able to interpret what the null is and what rejecting the null is relative to the interesting problem at hand. The relationship between type 2 error and statistical power and effect size. So if you make the effect size larger, what happens to these things, that sort of thing. Understand the relationship between standard deviation and standard error, confidence intervals, prediction intervals, all of that. So any questions about stats, those terms? Then this is, I think, where I thought I had it earlier. So this is just, this is the ones that you should probably worry about. That last slide that I pulled in. This is the kind of longer list. But I've kind of summarized, like the normal will be one that I would think you should probably feel pretty comfortable with. The exponential you should feel comfortable with. The Weibull you should feel comfortable with, and the Poisson you should feel comfortable with. And you should be able to discriminate between them. So if I give you a description of data that would be more likely modeled by one than the other, you'd be able to pick between these four. Then QQ plots, like be able to sort of know how a QQ plot is a graphical way of assessing goodness of fit. So we talked about how you start with QQ plots and then you finish up with PP plots. And then we've talked about how you do point estimation and the maximum likelihood for distribution parameters, which are kind of the next step up. So we've got the summary statistics. So these are the formulas I was mentioning earlier that you should probably know, but I'm probably not going to force you to do heavy calculations of these. But you should generally know that the summary statistics have their own sampling distribution and they're only estimates. And that's why we really need intervals and not just point estimates. And then the distributions have their own parameters, and we need our own ways to estimate them, and those maximum likelihood methods do that. I'm not going to ask you to do a maximum likelihood estimation, but you should generally know that these maximum likelihood estimators exist, and so that there are formulas that you could look up that provide the maximum likelihood estimate of each parameter for these distributions. So if you want to know these, that's fine. I don't really care if you've memorized these. But I generally sort of am interested in your idea or you knowing that maximum likelihood exists as a way to estimate parameters when you have a parameter that's not just a simple summary statistic. So question?
In the review ICA, we did have to figure out the exponential.
Sure.
So
I would say that I think that for the final, I'm not going to make you hand crank out a maximum likelihood. I just maybe do that in the ICA just to kind of get a better appreciation of what's going on in the maximum likelihood. Okay, so chi-squared test, know how to do a chi-squared test for the general case. So the big important thing here is that the expected number in each interval is the number of total samples times the probability that you could have landed in that interval. So I might give you a CDF. And if I give you a CDF, then you sort of, I would say, maybe I'll write that in. is that if I generally try to make these problems so that you don't have to spend a lot of time on each problem. So if you're doing a chi-squared and I give you a CDF, say F, and I say to calculate, let's say you have to calculate the number in an interval that goes from 2 to 3. So you might be tempted to take the CDF and then take its derivative to get the PDF, and then try to take an integral of the PDF from 2 to 3. But if you did all of that, then that would just be the same as doing the CDF evaluated at the two boundaries. And so that gives you the probability of landing in that interval, and then you can just multiply that by the number of samples, and this gives you your expected number that land in that bin from 2 to 3. And so, yeah, so just generally know how to quickly calculate expected number of outcomes that land in intervals, and look for tricks like this that I'm probably not going to make you do a long interval. And so if you feel like you're doing an interval, it's taking you a long amount of time, then maybe there's alternative approaches. Yeah.
That's the only difference, right?
In the chi-squared versus like what we did pre-midterm, that is one major difference. The other difference is how we calculate degrees of freedom. And so you have to subtract it's not only the number of bins minus 1, but you also penalize by the number of estimated parameters. So as long as you adjust for the degrees of freedom and properly calculate this expected number, it works just like what we did for the midterm. And then also similarly for the Komagata-Smirnoff test, it looks just like the midterm one, but instead of plotting your data down this row here, you take your data, sort it, and then plug it into its CDF, or the hypothetical CDF, and then you plot the hypothetical CDF's values down the middle here, but otherwise it's identical to what you did pre-midterm. Yeah.
I'm just curious, so regarding the inverse transform technique, could that be ever applied for finding optimal values to simulation problems?
Well, I mean, so the inverse, I don't exactly know. I don't exactly have in mind what you have in mind, but I mean, when you run a sim, you're always effectively using the inverse transform behind the scenes. It's always, like if you had maybe a CDF, a sample CDF of outcomes from a sim, then maybe you could use an inverse transform model to sort of generate a meta model of your simulation. So your simulation took several weeks to run, but you get a consistent distribution of outputs, so you could get rid of that sim and just not run the sim at all and just sample from it. Well, looks like we are out of time. If there's any other questions, send me emails or come up to me after class, and just give everybody attendance for today. Good luck.